In particle physics, a glueball is a hypothetical composite particle. It consists solely of gluon particles, without valence quarks. Such a state is possible because gluons carry color charge and experience the strong interaction. Glueballs are extremely difficult to identify in particle accelerators, because they mix with ordinary meson states. Theoretical calculations show that glueballs should exist at energy ranges accessible with current collider technology. However, due to the aforementioned difficulty, they have so far not been observed and identified with certainty. Although phenomenological calculations have suggested that an experimentally identified glueball candidate, denoted, has properties consistent with those expected of a standard model glueball. The prediction that glueballs exist is one of the most important predictions of the standard model of particle physics that has not yet been confirmed experimentally. Glueballs are the only particles predicted by the standard model with total angular momentum that could be either 2 or 3 in their ground states. Properties of glueballs. In principle, it is theoretically possible for all properties of glueballs to be calculated exactly and derived directly from the equations and fundamental physical constants of quantum chromodynamics without further experimental input. So, the predicted properties of these hypothetical particles can be described in exquisite detail using only standard model physics which have wide acceptance in the theoretical physics literature. But, there is considerable uncertainty in the measurement of some of the relevant key physical constants. And the QCD calculations are so difficult that solutions to these equations are almost always numerical approximations. This can lead to variation in theoretical predictions of glueball properties like mass and branching ratios in glueball decays. Constituent particles and color charge. Theoretical studies of glueballs have focused on glueballs consisting of either 2 gluons or 3 gluons, by analogy to mesons and baryons that have 2 and 3 quarks respectively. As in the case of mesons and baryons, glueballs would be QCD color charge neutral. The baryon number of a glueball is 0. Total angular momentum. 2 gluon glueballs can have total angular momentum of 0 or 2. 3 gluon glueballs can have total angular momentum of 1 or 3. All glueballs have integer total angular momentum, which implies that they are bosons rather than fermions. Glueballs are the only particles predicted by the standard model with total angular momentum that could be either 2 or 3 in their ground states. Although mesons made of 2 quarks with J equals 0 and J equals 1 with similar masses have been observed, and excited states of other mesons can have these values of total angular momentum. Fundamental particles with ground states having J equals 0 or J equals 2 are easily distinguished from glueballs. The hypothetical graviton, while having a total angular momentum J equals 2, would be massless and lack color charge, and so would be easily distinguished from glueballs. The standard model Higgs boson, for which an experimentally measured mass of about 125 to 126 GeV c² has been determined, is the only fundamental particle with J equals 0 in the standard model, also lacks color charge and hence does not engage in strong force interactions. The Higgs boson is about 25 to 80 times as heavy as the mass of the various glueball states predicted by the standard model. Electric charge. All glueballs would have electric charge Q of 0 as gluons themselves do not have an electric charge. Mass and parity. Glueballs are predicted by quantum chromodynamics to be massive, notwithstanding the fact that gluons themselves have 0 rest mass in the standard model. Glueballs with all 4 possible combinations of quantum numbers p and c for every possible total angular momentum have been considered, producing at least 15 possible glueball states, including excited glueball states that share the same quantum numbers but have differing masses, with the lightest states having masses as low as 1.4 GeV c², and the heaviest states having masses as great as almost 5 GeV c². These masses are on the same order of magnitude as the masses of many experimentally observed mesons and baryons, as well as to the masses of the tau lepton, charm quark, boson quark, some hydrogen isotopes, and some helium isotopes. Stability and decay channels, just as all standard model mesons and baryons, except the proton, are unstable in isolation. All glueballs are predicted by the standard model to be unstable in isolation, with various QCD calculations predicting the total decay width for various glueball states. QCD calculations also make predictions regarding the expected decay patterns of glueballs. For example, glueballs would not have radiative or two-photon decays, but would have decays into pairs of pions, pairs of kaons, or pairs of atomesons. Practical impact on macroscopic low-energy physics. Because standard model glueballs are so ephemeral and are only generated in high-energy physics, glueballs only arise synthetically in the natural conditions found on Earth that humans can easily observe. They are scientifically notable mostly because they are a testable prediction of the standard model, and not because of phenomenological impact on macroscopic processes, or their engineering applications. Lattice Qcd Simulations. Lattice Qcd provides a way to study the glueball spectrum theoretically and from first principles. Some of the first quantities calculated using Lattice Qcd methods were glueball mass estimates. Morningstar and Pedden computed in 1999 the masses of the lightest glueballs in QCD without dynamical quarks. The three lowest states are tabulated below. The presence of dynamical quarks would slightly alter these data, but also makes the computations more difficult. Since that time, calculations within QCD find the lightest glueball to be a scalar with mass in the range of about 1000 to 1700 MeV. Experimental candidates. Particle accelerator experiments are often able to identify unstable composite particles and assign masses to those particles to a precision of approximately 10 MeV c², without being able to immediately assign to the particle resonance that is observed all of the properties of that particle. Scores of such particles have been detected, although particles detected in some experiments but not others can be viewed as doubtful. Some of the candidate particle resonances that could be glueballs, although the evidence is not definitive, include the following: vector, pseudo-vector, or tensor glueball candidates. X observed by the Barbar collaboration as a candidate for an excited state of the 2+, 1+, or 1 glueball states with a mass of about 3.02 GeV c². Scalar glueball candidates. F0, also known as sigma. The properties of this particle are possibly consistent with a 1000 MeV or 1500 MeV mass glueball. F0. The structure of this composite particle is consistent with the existence of a light glueball. F0. Existence of this resonance is disputed but is a candidate for a glueball meson mixing state. F0. Existence of this resonance is undisputed but its status as a glueball meson mixing state or pure glueball is not well established. F0. Existence of this resonance is undisputed but its status as a glueball meson mixing state or pure glueball is not well established. Other glueball candidates. Gluon jets at the LEP experiment show a 40% excess over theoretical expectations of electromagnetically neutral clusters, which suggests that electromagnetically neutral particles expected in gluon-rich environments such as glueballs are likely to be present. Many of these candidates have been the subject of active investigation for at least 18 years. The GlueX experiment, scheduled to begin in 2014, has been specifically designed to produce more definitive experimental evidence glueballs.